And next up in our webinar series here is Dr. Michael Barker, who will be presenting on next gen steel bridge design tools for smarter solutions. So he's debuting a pretty cool design tool. Dr. Barker received his BS and MS in civil engineering from Purdue University and his PhD from the University of Minnesota. He's a professor of civil and architectural engineering at the University of Wyoming. And Dr. Barker is also the director of education for the Short Span Steel Bridge Alliance. And with that, I will turn
All
it over
right.
to you, Michael. The floor is yours.
Thank you, John. Thank you for the good introduction and description of our programming here. Like John said, we're going to talk about a new design tool today called eBeam 140 that we're pretty excited about. But I want to talk about different resources you have when you have a 60-foot span or a 100-foot span or whatever that you need a bridge for. There are resources out there through the Short Span Steel Bridge Alliance with eSpan 140 that will give you a preliminary simple span design or a modular design for rolled beam bridges or plate girder bridges, press brake tub girder bridges, and even buried bridges. And that's a web-based tool that just literally just takes a couple minutes to find a preliminary design. Then the National Steel Bridge Alliance has what's called LRFD Simon, which truly is an optimization design packet for plate girders and tubs. And its strength really comes in where it can do multi-span bridges, and so I certainly encourage you to look at those two resources. But today we're going to present for the first time ever this new Short Span Steel Bridge Alliance eBeam 140. It is an Excel-based rolled beam design software packet for non-composite and composite simple span W-shaped steel bridge design. And there's a website there for you to go and download it on your own. But I'm going to start with a demonstration. We're going to look at a non-composite bridge first. That's 52 foot long, has a couple lanes. We'll see why, but we're going to try 6 girders at 5.5 foot spacing with a 1.25 foot overhang. Some barriers that only weigh 50 pounds per foot with this, the nice slim barriers for non-composite bridges. Roadway width of 28, bridge width of 30. Only one diaphragm right in the middle. It is going to be considered unbraced. To begin with, we're going to look at bracing later. We're going to put a corrugated metal deck on top of it with gravel with a load of 80 PSF. No additional DC1 or 2 loading, no wearing surface, no construction load since we're just going to cantilever out that uh, uh, corrugated metal deck. We are going to consider 5% extra for diaphragms and stiffeners and things like that. We want to build it out of 50 KSI steel. We want the span to depth limit and a minimum depth for constructability and diaphragms. We are going to look at the L over 800 deflection limit, even though this could be considered a rural bridge, and maybe that optional deflection limit does not apply. Like I said, we're going to consider the compression flange not braced to begin with. We are going to use the inelastic capacity of AASHTO Appendix A6. We're going to only have 200 average daily truck traffic in a single lane, which makes this a fatigue 2 or a finite life fatigue design. And we don't have a user vehicle, just the HL93. Whoop. And so here is what you see. Well, here's more or less what you see when you get into the working part of eBeam 140, where the blue and the green are inputs for us. Of course, the blue is different color because you start off by saying this is a non-composite bridge. It's going to be 52 feet long, 28-foot roadway width. I want 2 stripe lanes. My barrier width I want to be 1. And then we came up with the 6 girders at 5.5 feet with this little helpful table here that says if you have 4 girders, this is what it should be, 5, 6, 7, 8, 9, whatever. This can design up to four lane bridges, so you can get up into some larger spacings. So in here we put 6 girders at 5.5 feet with an overhang of 1.25, and that gives us a roadway width of 28 and a bridge width of 30. Then we come down here and we have lots of choices for what kind of non-composite decks on there. We are going to choose the corrugated metal deck. All of these have different live load distribution factors, and it's going to weigh 80 pounds per square foot. Down here is for composite. We'll look at that a little bit later, but it's just ignored here. Here's our fatigue, 75-year fatigue life at 200 ADTT single lane. And we do not want a user-defined truck. But if we did, all we would have to do is change that to yes. And I've got in there a typical logging truck. Over here, again, we have to make sure we fill in the green. We don't have any additional DC1. We will on the next bridge. Our railing, our bridge railing weighs 50 pounds per foot, and we're sharing that with the two outside girders, and then no wearing surface, but there's the 5%. Now, a big part of design nowadays is construction loading, and since we're cantilevering that out, we don't have any lateral flange bending construction type loads. Then we move on to the characteristics of the material and that type of thing, and we want 50 KSI. This is just repeat of some we put in. And we put in the diaphragm spacing. We only have one diaphragm at 26, and we put the end of the bridge in there. Yes, we want to use Appendix A6 to get that extra capacity. Yes, we want the program to calculate CBs, and we don't want to put them in by hand. Yes, we want to consider W40 and 44s, but we can get rid of that. L over D's, minimum, maximums, L over 800. No, the flanges, the compression flange is not braced. And so we just input what we're looking for the bridge. We come over here and we hit this run design, and it is going to check every W shape that AISE lists and find and then rank them in terms of weight. So right here it says a W36 by 135 meets the strength 1 service 2 and construction, also meets fatigue, and also meets the deflection limit. And we'll talk a little bit more about that a little bit later. Over here, we have kind of a summary of the design and some more information on the performance ratios for strength and service and constructability that we can look at a little bit to see if we need to modify something in the design. And that can happen in the second sheet called Select a Girder. For instance, we saw that the W36 by 135 was the lightest section. But we also see over here on the right that a W33 by 141 also meets all the requirements. And for 6 pounds per foot more, we can decrease the depth of the structure by 3 inches. A 27 by 146 meets all of them except for the deflection. Well, if deflection's not that important, and we'll look at this again later, we can get rid of 9 inches of depth. But this sheet shows that, yeah, the strength 1 controlled the overall design at 0.993. Wow, that's right at near 1. Service 2 is lower. Construction, since we don't have those construction loads, are low. Fatigue, not really a problem, only at 0.6, and then the deflection, it made that also. But here's the performance within the 2 unbraced lengths. And we can see that our moment capacity over our yield moment is pretty low because we have those high unbraced lengths or large unbraced lengths. And then, of course, there is a summary sheet that goes through, and it'll give us the service 2 loads, capacities, section properties, and performance ratios there, the live load deflection ones, the fatigue, which only checks at actual shear stiffener or connection plate stiffeners, the strength 1 or 2 at the shear or for shear at the support. It also gives the strength information by unbraced length, the construction, the dead load deflections, and then even the abutment reactions. So we went through that and we found, hey, a W36 by 135 is the lightest W shape that will meet all of the AASHTO criteria for what we consider. And what controlled was the strength 1 limit state with a performance ratio of 0.993. So now let's talk about the software a little bit. Yes, it's Excel-based. It's a rolled beam design software. It can do non-composite or composite design. It can consider all sorts of different steel yield stresses in case, a county might have some older beams that they got from the state that might be 33 or 36 that they want to consider. We put in the basic bridge layout. The diaphragm is variable along the span. It can have any decking that's part of AASHTO, wood, grid, corrugated metal deck, non-composite concrete, composite concrete. And then, of course, it does the HL93 AASHTO loading, but we can also put in a user-defined vehicle. And there I put in like a logging truck. The diaphragm spacing is variable along the span. You can have up to 7 unbraced lengths, which means we can even design for skewed bridges with the actual diaphragm spacings. The compression flange bracing during construction can be set and for the final state. Like I said, any decking, wood, grid, corrugated, non-composite, composite. For composite, the F prime C, we can have a full depth deck or stay in place forms that reduce that, variable haunch, a sacrificial surface, shear connector design. We can add additional DC-1 loading, like for the overhangs, which are sometimes different than between the girders or for utilities. We have variable bridge railing, where we can assign how much it is and where it goes. And then the steel beams are individually considered in the dead load uh, for dead load force effects. We can put a wearing surface on there. We can add additional DC2 loads after it's composite with utilities or whatever. For the vehicle loading, yes, it does the AASHTO HL93 truck, tandem and lane, but we can also put in a user-defined vehicle. And we can even characterize how we want that considered. We can use, we have a variable user live load factor. For instance, if we have a one-time pass or a rare pass of a logging vehicle, we don't want to design it for strength 1. We want to design for strength 2, where the live load factor is lower. We can put an optional lane load on there. We can use single or multi-lane distribution factors. Like that logging truck, when it goes over our bridge, there's not going to be another truck next to it. So we're probably going to use single lateral load distribution factors. And we can even put in a user input impact factor. For live load distribution factors, of course, it does all the AASHTO criteria for moment and shear, but that varies on decking and composite versus non-composite. A lot of times we use the lever rule and it does that automatically if necessary. We do single and multi-lane lateral distribution factors for strength and fatigue and deflections. We also do that rigid rotational analysis that is more or less required in AASHTO. And then we also have the opportunity to put in user input live load distribution factors. Like you saw when I ran the thing, we can limit span over depth ratios. We can put in minimum depths because we have certain size diaphragms that we like to use. We can put in maximum depths if we have approaches that we don't want to raise or clearance issues. We have an option on whether it should consider W40 or 44 because those are not as common as other types of shapes. We can put in a user-defined deflection limit. Now, in AASHTO, deflection limits are optional. The traditional ones are L over 800 if there's no sidewalks, L over 1,000 if there are. But they are optional. We're going to take a little look at that, and we can add a percent steel for miscellaneous for the stiffeners and the diaphragms. It applies AASHTO 610.8 or Appendix A6, and there's been some changes of that. This does meet the requirements of AASHTO Edition 10, and there's some changes in there for that one. Calculated CBs, the moment gradient factor for lateral torsional buckling. It calculates those for every unbraced length. And again, AASHTO made a significant change to that in Edition 10, or you can put in your own CBs if you want. It will do fatigue 1 or fatigue 2 based on the ADTT in a single lane, and those have changed under AASHTO 10. You can also do a variable design life. You can, the standard is 75, but you can put in whatever you want. So the program performs dead, construction, and live load analysis for each unbraced length. Then it does a strength 1 or strength 2 check, a constructability check for each of the unbraced lengths. Near the middle, it's going to do a service 2 at the maximum moment. It's going to do a fatigue at the critical diaphragm location, which it just assumes that it is a detail C prime. And then if it's composite, it's going to do a strength and fatigue shear stud design, which again has changed considerably under AASHTO 10. So here we are. We saw this when I ran the program. What the program does is it determines all W shapes that meet strength 1 or 2, service 2, and construction performance ratio. That's the left column there. And we see, yeah, W36 by 135 meets all those. Then it looks at fatigue. Does it also meet fatigue? And if it does, it'll put that shape there. And then it looks at deflection. And if it does, it will put its shape there. And then it has a little bit of information there. So that's how we came up with a W36 by 135. But as I said, we could go to a W33 by 141 with only 6 pounds per foot more and lose 3 inches. Or we could go to a 27 by 146 if the deflection is not an absolute criteria, because that has a deflection of L over 761, not much over the 800. And then, of course, that second sheet allows us to play with that and look at that and examine that. You know, it gives the strength performance ratios, the service, construction, fatigue, deflection. It gives us the unbraced lengths, and it gives us this MN, the moment capacity we're using versus MY. And that's a little low, but we can use this to change diaphragm spacing or look at something other than the lightest weight solution or other readily available sections if a county has a bunch of sections in their yard and say, hey, does this 24 by 104 work here? Then, of course, you saw that it has the results page. It's a design summary, all the superstructure design results specific to limit states for the unbraced lengths and et cetera. It has all those up there. And you see what you saw in the file here. It has dead load deflections so that we can specify cambers. It also has abutment reaction cases for multi-lane. And if we look at those, you know, DC1, yes, that's at the center line of the abutment. DC2, the wearing surface, which is nothing. But if we have a single lane truck on there, we're going to have a lower load, but at a higher eccentricity from the center line, which can be important for abutment design, pier design, or pile design. Or if we have 2 lanes loaded with a different multi-presence factor, yes, the load goes up, but it goes closer to the center line. And of course, when we're designing that abutment, we need to consider those different things. But up here under strength, we have the unbraced length, the DC1, 2, and wearing surface loads, the HL93 live load plus impact moments. Now, if I had a user truck, it would be in this next column with its live load factor and its values. And then it calculates an ultimate moment, a CB, an MN, and a performance ratio. And then same thing for under construction. Not very important here because all we have for construction more or less is DC1 loads. So that's it. We looked at that, and we're going to continue with this demonstration to show some of the power we have when we have a program like this. When we put it in, as is stated here, it came up with a W36 by 135. But what if I considered a different diaphragm spacing? Or what if I considered that a corrugated metal deck, we're going to attach that to the top flange well enough to where that top flange is braced? Or what if I had a user-defined vehicle? And so here's the first case I'm going to look at. The left side here is the original, 2 unbraced lengths, LCB 26 foot, just HL93 unbraced within the unbraced lengths. And that came up with a W36 by 135. But if I add an additional diaphragm, or in other words, I'm going to have unbraced lengths of 19 feet, 14 feet, and 19 feet instead of just the 2 unbraced lengths. Now we can see down here when I rerun that thing and go to this page, now I can see I'm using much more of the moment capacity because I've shortened those unbraced lengths. And my strength, or this one was controlled by the strength ratio, but because I'm using more of that moment capacity, I can go down to a W33 by 118 to meet strength 1, service, and constructability. That would save 5,400 pounds compared to the original design. But I do need an additional diaphragm. Yeah, that's true. And we see that the deflection, whoa, what happened here? The deflection has a performance ratio of 1.009, which gives us a live load deflection of L over 793. So we'd have to say, yeah, that's okay. We're not going to keep the L over 800 an absolute. We can go down to L over 93, and we can go with a W33 by 118. To meet the deflection limit and everything else, we would need to go to a W33 by 130, which is still less, but not as big a savings, not 5,400 pounds. Okay, so let's set that one to the side. Now let's say, hey, we're going to build that bridge to where the corrugated metal decking is actually going to laterally support that compression flange, and my unbraced length is 0. Well, here's the original with the unbraced lengths and the low moment to MY capacity that we're using. Here's a new one. It still shows the unbraced length segments, but we can see that we have much higher moment to MY. In fact, we are in Appendix A6 where we can get that RPC and RPT to get above the yield moment. And that brings us down to a W30 by 116. That's 6,000 pounds of steel saved if we can consider that the corrugated metal decking supports that compression flange. Now, again, we violate that L over 800 by a little bit. We're at L over 663. But if this is an off system bridge, or if we're not going to enforce the deflection limits, and L over 663 is not far off of that, we can get this all the way down to a 30 by 116, save 6 inches and 6,000 pounds because we are able to do these what if questions. Okay, what about this logging truck that I kept talking about? If we had a logging truck that weighed 160,000 pounds and had 5 axles, I'm not showing the configuration. That's enough information we need. And here is the original design again, still with only the diaphragm at the middle. And this is the HL93 design, and it says W36 by 135. If we add this big truck, what does it do? Well, over here, the strength limit controlled, and over here, we can see that, yeah, because of that, this truck might do more moment, more shear, whatever, and that we might have to change sections. And if we use a live load factor of 1.35, which I would support, no lane load, which I would support, single lane lateral distribution factors, and kept it unbraced, it goes up to a W36 by 150. Okay, not too bad, 15 pounds per foot for putting a 160,000 pound truck on there. If we were conservative, we just said, hey, we're just going to treat this like the HL93 and did it under strength 1 and still used 1.75. But we were smart enough not to put the lane load on, but we still wanted to use the multi-lane distribution factors and still consider it unbraced. It goes up to 170. That's costly. And I don't recommend number 2. But number 3, if we do the first thing, consider it strength 2 with 1.35, no lane load, single lane, and we said, hey, that corrugated metal decking, we're going to attach it to where it's braced. We actually get down to a 33 by 130, less than the original. And so this program allows us to do all of these different types of changes and do it very quickly. So now let's look at a composite bridge. This one's 62 foot long, still 2 traffic lanes. But with composite bridges, we don't like those narrow girder spacings. We like to get them out a little way. So we're going to look at 4 girders at 9 foot spacing, overhang 2 foot. Barriers, now we're going to put maybe, some jersey type barriers on there that weigh 250 pounds per foot, and they're 1.5 foot wide. Roadway width 28, which means our bridge width goes up to 31. I am going to put diaphragms at 21 and 41 feet, and we'll see the unbraced lengths from that. It's going to be an 8-inch structural deck, 1/2 inch sacrificial surface, which does not add to the capacity, a 2-inch haunch from the top of the web, 2-inch stay in place forms, which weigh 15 PSF, and 7/8 inch shear studs with 4 KSI concrete. Because I'm going to shore up that overhang, I'm going to have some extra weight there. I estimated it was 40 pounds per foot, and I'm going to put it 100% on the critical girder. I am going to consider for a future 25 pound per square foot wearing surface. I am going to put a construction load way out there at the end of the overhang of 275 pounds per foot, plus a concentrated load of 3,000. I do want to add a little bit for diaphragms. Again, this is pretty much the same, 50 KSI steel, L over 800. Compression flange is not braced for construction, but of course is for the final state. I am going to use Appendix A6 for that. Here, this is a pretty busy bridge. I have a ADTT single lane of 1,000, which means this is an infinite life fatigue design, and I'm not going to put a user design vehicle. And I showed the answer here. I will go to the to the program. Here it is. So I put in the 62, the 28, the 2, the 1.5, and I said 4 girders at 9, and that comes from right up here with my little helper table there and a 2-foot overhang. Now it's going to ignore the non-composite bridge information. It's going to go down here, and there's my 8-inch deck, my sacrificial service, my haunch. Yes, I'm using SIP. This is how much they weigh. That's how deep they are. There's my studs. Here's my fatigue. Yeah, it tells me fatigue 1 controls for infinite life. There's the extra DC1 that's going to be on my girder. Here's my barrier that I'm going to share between the exterior and the adjacent girder. I don't have additional DC2, but I do have wearing surface. And here are my construction loads. This is, of course, similar from before. I'm going to use 50 KSI, but now I've got a diaphragm at 2141, and of course the far end is 62. I will consider W40 and 44s for this one. I do want 12-inch minimum, 44 maximum, L over 800. It is not braced for construction, but it is braced in the final state, even though if this stays no, it's going to assume it is. And then I come over here and hit run design, and it says, hey, now this is just a coincidence. It says W36 by 135, which of course was by non-composite, but that's just a coincidence. But again, we see if we want to save 3 inches, it could be a 33 by 141. If we want to save 9 inches, no, I can't use that 27 by 146 anymore because it doesn't meet fatigue. If I wanted to save 9 inches, I'd have to come down here and make it a 27 by 161. That's pretty costly. That's a lot. That's 26 pounds per foot extra just to save 9 inches. But we can look at all those things. We still have the same information over here as we did for the non-composite. I can still look at different girders. For instance, if I wanted to look at that 33 by 141, I just drop down and say, hey, show me the results for that one. And then if that's what I want to pick, and I go to final design, that's what it's going to show me, is the one I pick and select a girder. And so here it's saying W33 by 141, and here's all the results for that. Yeah, no, I'm going to stick with that 36 by 135, come back over here. Now it gives me all the results for 36 by 135. And these are all the same as we saw before, except this is composite, so it is going to do the stud design. So here we are coming back. We just went through the program. W36 by 135. Fatigue controlled this one, and the fatigue ratio was 0.961. So if we look at that, here's that table I showed, but if we look at that selector girder, yeah, the strength performance ratio is only 0.79. The service 2 is only 0.88. Construction, whoa, that's pretty high. That's right. When we have those big loads out at the end of a overhang and we're putting those knee brace brackets in there, it puts quite a bit of lateral flange bending into our top and bottom flanges that we have to consider in the design. And that came in with a performance ratio of 0.95. Fatigue, that's the controlling one, and deflection, no problem. And again, we can come down here and say, oh yeah, we're using lots of over MY because it's composite, but we have 21, 20, and 21 foot unbraced links here, and the strength 1 performance ratios there, and the CBs. Okay, so here's that results page, and we are looking at it for a W36 by 135. The overall performance ratio is 0.961, fatigue controlled, but we can go look at all of them. Here's the service 2, there's the DC1 moment 2, wearing surface, the HL93 plus impact, and of course it produces stresses based on the steel only section, the long composite steel section, or the short-term, the long-term composite, or the short-term composite section modulus, and it calculates a stress, and it has a capacity of 0.95 FY, and there's the performance ratio. For live load deflection, it has a deflection of 0.57. The allowable with L over 800 is 0.93. Deflection performance ratio 0.62. Fatigue at the critical brace, which is not at the center line, it's at 21 feet. There's the fatigue moment and the fatigue section modulus, which is at the top of the bottom flange, and the fatigue stress, and the fatigue allowable, and the fatigue ratio. And of course, those will change whether it's fatigue 1 or fatigue 2. For the strength, for the shear check, this is not really reported very often here because shear is not going to control in W-shaped beams. Plate girders, yes, but not W-shaped beams. And so we see that performance ratio is 0.353, and then a summary of all the information. If I had a user vehicle, all of that information would be right here. Oh, it also reports out the live load distribution factors for single lane and multi-lane, fatigue, and shear. Then it continues on with the strength 1 or strength 2 check, where it looks at each unbraced length, gives the DC1, 2 wearing surface moments, the HL93 with the 1.75 load factor for strength 1. Here would be the user vehicle, and then whichever one control would become the M sub U with a CB that determines an M sub N, and then a performance ratio. So we can track all of this. So the engineer can verify all of this, because this program is not going to give you signed design plans. And then the construction here did become important. There's the strong axis construction moment, which does include the additional construction loading, which is a little different than some other programs. There's the lateral flange moment. There's the amplification factor because of P delta effects. And those are pretty high, we see. Why? Because we have pretty long unbraced lengths. And there's the P delta stresses in there. And here's the checks for those and the performance ratios. And yeah, construction can control design. And then, of course, the dead load deflections for, where the DC1 is on the steel moment of inertia, the DC2 and the wearing surface are on the long-term composite section. Again, it does the abutment loads with the dead loads and the single lane and the multi-lane. And if we had 4 lanes here, it would have 3 lane and 4 lane also. Also gives you this nice little chart to where it gives you the nominal moments on the girder for DC1, 2, wearing surface, HL93, fatigue, and the user truck, the green one's down here at 0. But if it did have a user vehicle, that would be up here someplace. And it might control, it might not control. And then if it's a composite bridge, it will do the shear stud design according to AASHTO 10, which has given us quite a bit of leeway or quite a bit of savings in shear studs, where it will do a strength. We need 127 studs for strength, and fatigue, we need somewhere around 158. But here, if we just divide it up into the 10th or 20% points, here are the spacings for single pitches, double pitches, or triple pitches. And then it just kind of shows it graphically here. Okay, so that gave us that W36 by 135 on the left side here with the 3 unbraced lengths with unbraced compression flange during construction and of course braced for the composite. It gives us our performance ratios. If we added that user truck, and we were smart and we said, hey, we're going to consider it a strength 2, where we use a live load factor of 1.35, no lane load, single lane distribution factors, it still comes up with a W36 by 135. Because over here, strength did not control. Service did not control. And fatigue does not depend on the user vehicle. So yes, the performance ratio for strength 1 or 2 went up, but it was still controlled by that. And this is a powerful tool to know that we do not have to increase the section size just because we have a user vehicle. Okay, wow. Good, good, good. So to wrap this up, this is a simple span, rolled shape, bridge design, Excel file that will do composite and non-composite bridges. On the website that I'm showing down there a little bit below, there is a user manual and examples. It's going to be, well, actually it's released now. Dan Snyder, our director, just finished the website this morning. It's released on shortspansteelbridges.org, where you go under a heading and you can go to eBeam 140, or you can go directly there. And it is ready for beta testing, is what we've decided to do. Now, we've already sent it out to, I don't know, about 10 different bridge designers, and they've come back, they've had some comments and things like that, and we think it's working. But just in case, we want to call it beta in case one of you download it and say, hey, Barker, this part's not working. And there's a place on the website that you can give us some feedback on there. And just to follow up, we are developing a simple span plate girder bridge design right now. That's also an Excel file. So here's what you're going to see when you go to the eBeam 140 page. It does say version 1.0 beta. You complete the form so that we can contact you with changes or updates or whatever. We know who has it, and you fill in who you are and who you work for and that kind of stuff. And you have to do this "I'm not a robot" thing, which I failed twice on before I could do it right. And it's going to send you an email in about 5 minutes that says, hey, click here and we will give you the path to download the Excel file. And of course, you want to check spam or clutter or junk folders, and you follow the instructions. And then you download it and you open it. Now, there is that macro in there that I push, which ranks them from lowest weight to highest weight on whether they meet the strength and the fatigue and the deflections. That's all that macro does, is goes to a sheet, ranks them according to weight, all the ones that work for strength, construction, and service too, and brings them back into those tables. So it is not malicious, but you are going to have to trust us if it gives you this warning that you have to open up. I forget. Well, it's blocked and there's a couple things you might have to do. But Dan Snyder built this page this morning that says, here's one way to do it. If it doesn't work, you might have to go to the Microsoft and say, hey, how do I unblock macros? And sometimes you have to do it by the folder and not just the file. But you can figure that out. And that's it. And I end with this one with a general invitation to visit our website, shortspansteelbridges.org, where you can subscribe to a weekly newsletter that comes out every Friday morning at 9:15 Eastern time that has all sorts of good information on it weekly. You can find a supplier if you have a 60-foot span and you want somebody to design, fabricate, ship you a bridge that you can just put together in a weekend. Those are all there. Of course, this design a bridge, you have the preliminary design with the eSpan 140 that'll give you a shot at it. And now we have this eBeam 140 that will really kind of optimize it. There's a little bit conservatism in there that you'll read in the user manual, but it is pretty much an optimized design. You can receive free project assistance or you can schedule a workshop webinar. Dan Snyder's listed here. He's the director of our Short Span Steel Bridge Alliance. Again, I'm Michael Barker, and I am the Director of Education for the SSSBA. And thank you for joining us today.